In this video, we want to answer the question, if you have an affine variety X inside AN, and you observe AN sits inside Pn, then what is the Zariski closure of X inside Pn? This thing is called the projective closure of X. And we have seen two examples already. So here inside A2, we had these two straight lines which are parallel. And then I claimed that taking the closure, we would get one intersection point exactly at this point here. And then similarly here, we drew some picture when we discussed cones of this vanishing locus of x1 squared minus x2 squared minus 1. And then again, the claim was that there you add points at infinity a and b given by these coordinates. But how can we do this systematically? Like, how can we actually calculate exactly which points we should add in this closure? Because, I mean, one thing that we do know is the closure never adds anything inside AN, because X inside AN is already closed. And so taking the closure there doesn't put in more points. The only thing that can be added is points in the complement of AN inside PN. And we have a candidate for the projective closure because we had already seen in the proof where we compared the Zariski topologies that when X is the vanishing locus of J inside AN, or J any ideal, then X is the intersection of the vanishing locus of JH, the homogenization of J, with the affine space. So this here is a Zariski closed set inside projective space, which contains X and which has the right intersection with affine space. So that's our candidate. And indeed, the next proposition says, in the situation as above, we have the projective closure is given by the vanishing locus of the homogenization of J. And if J is a non-zero principal ideal, then it's even true, then you don't have to take the homogenization of this entire thing, but in fact, you can just take the generator itself, homogenize it, and this will cut out the X bar inside Pn. So that's often very, very easy to calculate if you have just a single generator. So before we turn to the proof, let's actually do some example computations to convince us that in the examples we had, this gives the correct answer. So here, let's just take the projective closure of this y. It's a bit more interesting than x. So y is cut out by this equation, x1 minus 1. And by the part b, then the closure is just cut out by the homogenization, where you bump up this 1 to be an x0. And then what did we add at the line at infinity, the line cut out by x0? Well, this intersection is now cut out by both this equation and this. So this here, you see we can eliminate x0 using the second equation, and then it's just the vanishing locus of x1, x0. So it's the points where these two coordinates are 0, this one must be non-zero, and we can scale it to 1. So this indeed explains why this point here is in the closure. And then similarly, it's a bit more interesting equations. If we had this vanishing locus here inside affine space, then we homogenize like this, and then intersecting with the line at infinity again adds this equation x0 equals 0. And then we can eliminate this term, and we get an x1 squared minus x2 squared, which we can factor like this. And then, well, which points satisfy both of these equations? X0 must always be 0. And then either x1 is equal to x2, this gives you this point, or x1 is equal to minus x2, this gives you this point. So we exactly get these 2 points that we indicated here. So this is one example calculation like this. Okay, so let's turn to the proof. So we want to show X the vanishing locus of J, then X bar is the vanishing locus of JH. And we have seen, or somehow recall it by definition, the X bar is the smallest closed subset containing X. That's always true from topology. And we know this projective variety here is a closed subset of projective space containing X. So certainly it contains the smallest one. So X bar is always contained in here. then what we need for the rest of the proof of part A is to show the converse inclusion. So assume that you have some closed subset Y of projective space containing X. So Y is some vanishing locus of some homogeneous ideal J prime. Then we want to show that it is actually contained, or that this our candidate for the closure is contained in Y, because then it would be the minimal closed subset of this form. Now, well, we have an inclusion of such vanishing loci. This is contained in Y, which is the vanishing locus here. And then if you apply the IH on both sides, or the P, the projective vanishing locus on both sides, then we can apply the Nullstellensatz, because the vanishing ideal of the vanishing locus of something is just a radical. And the inclusion turns around because this was an inclusion reversing correspondence. And so here we would get that the radical of J prime is contained in the radical of JH. But in fact, I mean, the radical of J prime being contained in here is equivalent to just J prime being contained in here. That's enough because this is already radical. So as an upshot, we have reduced to showing that if this is true, then J prime is contained in the radical of JH. Okay. So let's get to work on proving this. So J prime is a homogeneous ideal, so it's generated by its homogeneous elements. So some G inside J prime. And our first claim is each of these G's had a very particular form, namely, they are all of the form some power of x0 times the homogenization of some polynomial in x1 up to xn. Okay. Let's see an example, and I hope from that example is more or less clear how you proceed. Let's look at this concrete G here. Then, well, you can certainly draw out as a first step as many factors x0 as you can. So in this case, you have an x0 squared, x0 4, so you can, of course, draw out an x0 squared factor. And then whatever polynomial remains has no common term x0, and then it's some polynomial. In this case, you would get an x1 to the 3 plus 2x2 x0 to the squared. And that's the homogenization of this polynomial. And in general, you can see if you have a polynomial, an x0 up to xn of some degree d, and it's homogeneous, and it is not divisible by x0, then it is always equal to the homogenization of its inhomogenization. That's the formal statement, but in this example, you can also just verify this equality here. And then I think once you do that, you can convince yourself that indeed this works. Okay, so we have manipulated this G to be in a particular shape, like this. And with this shape, we can now get to proving what we want. So we wanted to show J prime is contained in this radical. So J prime is generated by these elements G of this form. So let's show that all of these G are contained in the radical. And without loss of generality, you can assume G is not equal to 0, because we want to apply some homogenizations, and this would create problems. But of course, 0 is always contained in a radical, so that part is already done. And now we just have a very long list of implications. So first of all, G is in this J prime, and J prime cuts out Y, and Y contains X. And I claim this sequence of things means that G vanishes on X. That's just how the vanishing locus is defined. So G is a homogeneous polynomial. It vanishes on the subset X. This follows because X is contained in Y. And well, this X, if you remember, actually is contained in AN, the complement of the locus where x0 equals 0. And so in particular, on that locus X, the number x0 is never 0. And so this here vanishing on X is only possible if actually this FH vanishes on X. And then if we transfer this to these coordinates on these affine coordinates, then this tells you that this FH, the inhomogeneous, the dehomogenization of FH vanishes on F. This is basically, I mean, nothing super interesting has happened here, but we now see X no longer as a subset of Pn, but as a subset of An. And then we had to change coordinates. Basically, we had to set the coordinate x0 to be 0. But then one of the things we have seen, if you first homogenize and then dehomogenize, it doesn't actually change anything. So all of this, what this has given us is that F is now 0 on X. Okay, and so by definition, if F vanishes on X, then it is contained in the vanishing ideal of X. But now X was defined as the vanishing locus of this ideal J. So now J comes into business. And by the Milstein-Satz, IA of VA is equal to the radical of J. So we have concluded F is a radical of J. So in other words, some power of F is in J. Okay, that's just definition of radical ideal. And now we want to get back to the form here with the homogenization. And so one thing that we use is that by definition, now this being in J implies that its homogenization is in JH, because by definition of JH, this is the ideal generated by all of the homogenizations of things in J. So this explains this containment here. This is the construction of JH. And then when we introduced the homogenization, we saw it commutes with products. In particular, it commutes with taking some power. So this is the same thing as saying F first take homogenization, then the power. So we have that some power of FH is in JH. And then by definition of the radical, again, this means that FH is in the radical of GH. Okay, and this is almost what we want to show. We wanted to show that G is in the radical of GH, but G is equal to some multiple of FH. And so if this is in this ideal, then also this multiple is still in the ideal. So G is in here, and then we're done. Okay. So this was, I mean, this was not the most inspired proof, but we just had to kind of manipulate and exchange homogenization and powers and so on. So it was just some manipulation. Okay. And this was the first part. And then the second part is actually not so hard, because this was just the statement that if the ideal is actually cut out by a single, it's a principal ideal generated by F, then the projective closure is cut out by FH. But then, well, we know that it is cut out by JH. That was part A that we just proved. And so let's just compute JH, because I mean, the ideal generated by F is all of these elements F times G. G is a polynomial. So by definition, the JH is generated as an ideal by the homogenizations of all these things. And then we use again homogenization combines with products. So we have this. But now you see this is an ideal. It's generated by this FH times GH, where G runs through some polynomials. But certainly all of these are divisible by FH. And on the other hand, taking G equals 1, you just get FH on the nose. And these two properties imply that this ideal is actually just the ideal generated by FH. So here's the kind of the two inclusions separate. And that's what we wanted to show, because then the projective closure is cut out by this thing, but this is the same thing as this thing. Okay. So that was the end of the proposition. I just wanted to mention here that this taking the projective closure is what is behind some of the pictures that I had at the beginning of the last lecture as motivation, because there we saw if F is a complex polynomial of degree D in two variables, then I claimed inside affine space with the complex topology, the solution set looked like this surface of a donut with lots of holes. And then there are some kind of ends of this donut which go to infinity. So some sets of solutions which converge to infinity. And then we complained about the fact that this is not a compact set. It's not a very nice topological space. And now with this projective closure, we can actually see that this fills in these missing points. Because what just happens is these solutions go to infinity, and if you take them, instead of the equation f, you take fh, then what we have just seen, this is the closure of this inside this projective space. And what we see is this closure exactly adds these missing points in, because these d missing points are then the solutions of the equation fh of 0, x1, x2 on the P1 with coordinates x1, x2, and this is the P1 at infinity. Somehow, at least we can get an idea. I mean, this doesn't prove the full claim that I made, but at least we can get an idea how these extra points are filled in. They're just the points on the line at infinity.